Within Chapter 10, we explore a topic that I think you might have some prior knowledge of, which is gases. We're going to look at this in two different parts. Within this video, we're looking at characteristics of a gas, various gas laws, leading to what's called the ideal gas equation. Different characteristics of a gas. Like I said, I think you're probably familiar with different characteristics of gases. So here I give you some choices. Would you say a gas is more a homogeneous mixture or inhomogeneous? Are there strong attractions or weak attractions? For each of the options, consider is a gas more like something on the left or something on the right? I think you know about gases and probably have a reasonable model. Take a second. Are there any that you're confused about? Are there any comparisons where you're uncertain? This is my model for a gas. I view a gas as a homogeneous mixture where the particles are weakly attracted to each other. Most of a container of a gas would be empty space, and that means it's easily compressed. I can squish it smaller. And the particles themselves have unrestricted motion as they move about the container. Let's look and consider what's happening at the particle level. So suppose we have liquid water. It's in this closed container. And if we have a magnified view, if we zoom in, this is a description of what H2O looks like as a liquid. What if we had the same sealed container and the water had evaporated? What would a particle level representation look like now? What do you think? Is it more like A, B, C, or D? For H2O, I think I would be seeing discrete molecules. These discrete H2O molecules now have separated, so instead of being closer together as a liquid, they're now more spread out as the gas. I don't think I'm breaking any bonds. I think I'm simply separating the molecules further apart. A few elements are gases at ordinary temperature, things like helium or neon. We've also seen examples of molecules that are diatomic and gases at ordinary temperature and pressure. Nitrogen gas, oxygen gas are examples. Table 10.1 lists other common gases at room temperature. As I look at these, I'm seeing molecular compounds. Many molecular compounds are gases. I am also seeing that they are simple molecular formulas, low molar mass, things like ammonia, NH3. Nearly every gas that we encounter in this class is going to be a molecule similar to these. As we think about properties of a gas, does a gas have mass? Let's say we took a balloon, added gas to it. If we changed the mass, what if the balloon was filled with helium? What would happen to the mass then? Increase, decrease, or not change? I think the mass would go up. I'm adding more particles. The point here is we want to be careful. The mass is not the same thing as the density. I think as we added helium to that, the density would go down, the mass itself for the object would be going up. So in terms of properties, it does have mass. How about these other ones? Pressure? Pressure is the force divided by the area. We typically see units of atmospheres. 1 atm is also 750 millimeters of mercury, or 760 torr. Where that comes from is, imagine you have a container of mercury and this column that's sealed at the top. Atmospheric pressure pushes down on the mercury and causes it to rise up in the column. How high does it rise? 760 millimeters. That's the definition and the conversion between atm and torr. So if you have a value that's given in torr, you can do a simple proportion to figure out how many atm it would be. Make sure you're able to do conversions between both of those. Millimeters of mercury, which are also called torr, and atmospheres, which are atm. Let's think about gas that's in a balloon that we consider to be a flexible container. The pressure inside a balloon is different from the pressure outside of the balloon. Under what conditions? So we have this flexible container. When would the pressure be different? When the balloon's on Mount Everest, it's undergoing a volume increase, constant volume, or filled with helium. What are your thoughts? I think when it is undergoing a volume change, the pressure inside is not equal to the pressure outside. The force acting inside the walls are not the same as the force acting outside. When the pressure is different, the volume will change. Is this something you can visualize? You have a balloon where the gas particles inside are exerting a force, and gas particles on the outside are exerting a force. If the balloon is a flexible container and these forces are equal, the volume of the balloon does not change. So let's look at relationships between pressure, volume, the amount of the gas, and the temperature. Our symbols for that: pressure will be P, volume V, number of moles of gas is N, temperature T. Typical units will be atmospheres, liters, and in Kelvin. We need to be able to do temperature conversions between Celsius and Kelvin. 0 degrees Celsius is 273.15 Kelvin. We'll also see descriptions of what are called standard temperature and pressure. The pressure then is 1 atmosphere, and the temperature is 273.15 Kelvin. You might know some relationships between these, between things like pressure and volume, or temperature and volume. Let's explore those a little bit with the kinds of demonstrations that we can consider. We can learn a lot by using simply balloons, liquid nitrogen, and a vacuum pump. Let's see what happens if we place a balloon in a vacuum pump. A vacuum pump is removing the air from that portion of the bell jar. I'm seeing the balloon itself expand. If we release the seal, air can go back inside. The volume of the balloon changes once again. Why did the volume of the balloon increase? What would be your explanation? I think the pressure outside of the balloon was reduced. It was reduced because the air particles were removed from that bell jar. The pressure inside and outside the balloon were no longer equal. The force inside the balloon was greater than the force outside, and this led to the volume increasing. The volume of the balloon increases, and the pressure inside therefore decreased. If we think of those relationships, when the pressure goes up, the volume goes down, or vice versa. A linear relationship would be between the pressure and 1 over the volume. So what we're beginning to explore are different properties of gases, and key properties are back to the pressure, the volume, the amount of gas, and the temperature. With the ideal gas equation, we're going to bring all of those relationships together and see how that will be a useful model to make predictions for the properties of gases and connect it to other ideas that we've seen in this class, such as stoichiometry.